get started. I think you guys can probably hear me, but yeah, today we're talking about heaps and priority queues. That's our discussion for today. So let's dive into this topic. So first, I guess we're gonna talk about, maybe it's quiz 4 free response. We're gonna talk about a free response question. Then we're talking about hire the gator and pseudocode slides. And then we're gonna talk about heaps and priority queues. And we're gonna talk about heapify, which goes along with heaps. Yeah, heaps and priority queues are really cool topics. So I'm excited that you guys will be learning about them. Okay, I guess it's, yeah, quiz 4, but still an important question to know, I guess. And this question was, if you don't remember, sum by levels of a binary tree. So given a binary tree, the goal is to find the sum for each level of the tree and then put it into a vector. So yeah, and it was maybe kind of tricky, right? Maybe it's a couple weeks ago now, but if you think back to how it was, maybe it's a little tricky because you had to figure out a way to do a level order first, right? Because you want to find the sum at each level and then keep track of the sum at each level. So, but the main idea was, right, if you're doing a level order traversal, then at each level, you already know how many elements are going to be in that level because that's just the size of the queue when you start that level. So you can just, for each level, go through that number of elements and sum them and then put that into a vector. So if you're having trouble visualizing that, that's okay. You can go ahead and look at the pseudocode and talk about that. So for the pseudocode, notice that this is just, for the most part, a standard level order traversal. And what I mean by that is you're given a queue, right? And for this queue, if your queue which has a tree node, or a type tree node, and you have your vector of int for sums, and you push your root into the queue, and then while the queue is empty, and this is how we rarely do our level order traversal, you get the number of nodes at that current level, and that's just the size of the queue. Because if you remember, in a level order traversal, you never go to a level 2 levels down before you or never go to the next level until you finish this level. So at the exact moment when we finish the previous level, the size of the queue, right, is however many things are going to be in the following level. So that's just the num nodes queue size. That's why we can just loop over that, because that's going to be how many things are in this current level. And because that's the number of the current things in the current level, we can just, for each of them, add to our temporary sum and then put the temporary sum into our vector. And so that's kind of how this works. And then other than that, what's inside of this for loop here is just kind of standard in terms of how we do a level order traversal, in that we get the front of the queue, which is something at this level, the level we're currently at. We pop it from the queue. And then if it has a left child, we put its left child in the queue. So it's going to go to the back of the queue. So it'll be something we visit later, right, at the next time through this while loop. And then same thing with the right. But if it doesn't have children, then we don't put them in, right, in the queue. And at the end, right, because at each level, we kept track of the sum of the elements. At the end, since we've pushed back sum for every level, because this for loop goes through everything in the level and keeps the sum of all of them. At the end, the sum for every individual level is just the sums vector. So hopefully that makes some sense. And so we initialize an empty queue and return vector. And then if the root isn't empty, we push it onto the queue, right? And then, yeah, it's just going through for each level of the queue, get the size of the queue. So that's how many things, well, I guess, yeah, how many things were at the previous level, or how many things are at the current level, actually, yeah. How many things are at the current level, how many nodes there are at this level. And then we loop through the size of the queue, which just is going through every element at the level we're currently at. You add them together and add their children to the back of the queue. So that way, the next time through this while loop, that's how many things we'll go through. It's the thing is the next level. And that's it. Hopefully that makes some sense. And then we return something. Okay. So question about the quiz you can ask, but yeah, let's move on to the topic for today. And the topic for today, okay. Well, actually, that's right. Hire the gator first. So for hire the gator, so the goal of this is, yeah, it's basically to give you experience with technical interviews, but it's low stakes, which is good, right? So you meet with another student for 45, 60 minutes on Zoom, and you record the meeting and use Google Docs. Then you leave some time at the end to review. well, and what didn't. And yeah, there's an example here. This is, in my opinion, a pretty good assignment because technical interviews, especially your first time doing them, it can be a little overwhelming. So like having that experience, like even if it's not real, does kind of help actually. And here's some FRQ questions to prepare and review as good. Okay, but now we're gonna talk about the idea of priority queue. So maybe you can kind of think about this to yourself as the following. So I mean, it's a priority queue, so it's still kind of like a queue, maybe you're thinking. And maybe what we notice about a queue that we've talked about in the past, right? We talked about queues, which are just, standard queues. The way they order elements is just based on when you put the element into the queue, right? Like the first thing in the queue has the highest priority. So it's gonna be the first thing removed from the queue. And the second thing will have the second highest priority and so on, right? But like, what's stopping us from saying, instead of giving priority based on when an element was put into the queue, why can't we give priority based on how large the element is or some other criteria, right? Why can't we give priority based on something other than when we put the thing into the queue? Well, that's the idea of a priority queue, is like, rather than just having the priority set, as in a regular queue, we assign the priority based on just when you put it in, but a priority queue, you can basically define the priority however you want. And so, yeah, that's the cool thing about priority queues. They're just like an extension of queues. And yeah, it's a special type of queue. And you assign each element a priority. In regular queues, you do that too, but the priority is just when you put it in. And an element with the highest priority is dequeued before the element with the lowest priority. So just like with regular queues, the thing that has the highest priority is removed first. And elements with the same priority are handled based on the order they enter. So in that case, it just defaults to regular queue behavior. But yeah, now it's a priority queue, kind of like how stacks and queues are, they're abstract data types. So they define an abstract data type defines the properties and has multiple implementations. And then there's some functions of priority queues. And these are insert, peek, and pop. And these are just like the things we saw with stacks and queues, right? Where you can insert into a priority queue. You can look at the element on the top of the priority queue, and then you can pop from priority queue. And really, I guess this is more like the stack, because in a queue, well, no, I guess, yeah, it's more like the queue actually, because insert, I mean, it's similar to both, right? Where you only have access to like one element, where you insert, right? And you insert at one end, and then you peek. When you peek, you look at the top element, and then pop, you remove the top element or the highest priority element. So you, just like with stacks and queues, you only have access in terms of peeking and popping to that top element, like the element with the highest priority. You don't have access to the rest of it. And then there's implementations of it. And the main implementation, or one of the main ones, is like with an unsorted array or list. And this is with fast insertion and slow extraction, or this is one way of implementing it, I guess, rather, not a main one, but it's a way of implementing it, because you can use an unsorted array for a list. But that's kind of slow. I mean, yeah, it's great because you can just add it to the end of the array or list, which is good. But then when you actually want to take an element out, you have to go through the whole list and find it. So in this case, that's like O(n) time to extract, but O(1) time to insert. So maybe that's good. But another way is sorted array list, slow insertion, because you actually have to like maintain sortedness, and then fast extraction. So it's kind of slow to insert something, but kind of fast to extract it, because you have to insert, and maybe you have to resize the array, and then you have to, in terms of an array, right, you'll have to move every element over in order to make room for this one, because you want to put it in a specific place. So that might even be O(n) time to insert. And then extracting, though, you just have to do a binary search. So that would be like O log n. But both these are not really optimal, because you have slow extraction in one and slow insertion in the other. So maybe there's a better way of going about it. What if we can balance them? And rather than having like O(n) for extraction for unsorted and O(n) for sorted array insertion, what if we can balance them and use a heap? So what are heaps? Heaps are a good implementation of priority queues. And a heap is a tree-based structure, and it's a little bit different than like AVL trees or just balanced binary trees in general, because it's not a binary search tree, but it's still a tree, and it's still binary, well, generally we use a binary implementation of heap. So it's generally still a binary tree. But the idea of it is, the idea of a heap is that you have nodes in the tree that are higher up in the tree, so closer to the root, have a greater priority. And the root has the highest priority of all. So the way we track priority is just based on, or the way we keep track of priority is based on whatever's closest to the root, and the closest to the root of all is the root, right? And we use a heap ordering property. So you have max heaps and min heaps, which are both just heaps. Max heap just gives the high priority to the largest value. So if we're sorting based on value, right? Max heap gives priority to the largest value, min heap gives priority to the smallest value. So in a max heap, the largest value is the root, and in a min heap, the smallest value is the root. And the other thing is that it's basically determined based on the level you're at, right? So sort of anyway. So in a max heap, each node is going to be greater than both of its children, or all of its children if it's an n-ary heap rather than a binary heap. But yeah, in a max heap, every node is greater than all of its children. And in a max heap, and the root is the largest element of all, right? Because it's larger than its children, and then its children are larger than its children. So it has to be the largest of all, right? And in a min heap, since the priority is given to the smallest element, each node is smaller than its children. And so the smallest node of all is the root. So that's the idea of heaps, is we give different priority than just when you insert. It's based on like the elements themselves. And yeah, here we see some examples. So let's see an example of a min heap here. Notice this is a min heap because at each level, each node, the node's children are smaller than it. Or sorry, the node's children are larger than it. Each node, the children are larger, so the node itself is smaller than its children. So like this 10 here is smaller than 15 and 30, and 15 is smaller than 40 and 50, and 30 is smaller than 140. And notice, like, even if I change this to be like 35, it's still low, right? Because it's still okay, because it just has to be smaller than its children. But in a max heap, it's a little bit different because max heap is just the opposite. It's the same idea, it's just the opposite, because each node is larger than its children. So 100 is larger than 40 and 50. 40 is larger than 10 and 15. 50 is larger than or equal to 50 and 40. So this is still valid, even though the two are equal. But that's on a case-by-case basis, right? Like how we want to handle if they're equal. But well, something has to be. So this is kind of how I here. Okay, that's the heap data structure. So it's a little bit different than other kinds of trees we've seen, in that it really, each node, we only care about, like, is it larger than its children or smaller than its children? And so like that obviously, maybe you think really simplifies it, right? It's not as complicated as like an AVL tree, and that's absolutely true. So binary heap. So binary heap is just basically what we've been talking about. It's just a heap with only each node has at most 2 children, and it's complete. And the interesting thing about binary heaps are they're complete binary trees. And in general, heaps will be complete trees. And if you don't remember, complete trees are complete is that all levels are completely filled except possibly the last level. And at the last level, all the nodes are as far left as possible. So like, even if this 40 wasn't here, this is a complete tree. And even if this 100 isn't here, it's a complete tree. But I can't remove the 40, this 40, because that's not complete. Because this 50 isn't as far left as possible. Okay. And that's the idea of a complete tree, yeah, if you don't remember. And arrays, the way we usually implement heaps is with arrays. And arrays work really, really nicely. And we'll see why in a minute. But the other good thing about heaps is that the height of a heap is always going to be log n, always. Yeah, which is really nice, because all the properties of like, a lot of the properties which we remember from AVL trees, for example, one of the reasons why we cared so much about making it balanced was that we wanted the height to always be log n. Well, a heap, the height is always going to be log n. Now, it's not quite the same as an AVL tree because we don't have, like, it's not a binary search tree, but the height is going to be log n. That's a guarantee, which is really nice to have, and we'll see why in a minute. But pop, the reason why is because the height being log n ensures that pop and insert are both just log n. And about, yeah, you can only remove the root. So just like with regular queues where you can only remove the front of the queue, same thing is true with priority or heaps, which are basically priority queues, or priority queues are just heaps generally. So the same thing is true here, where you only have access to the top element, and removing it is log n. We'll see why in a minute. And same thing with insert. But hopefully that's just kind of an overview of heaps. Now I'll go into like some more details. Okay, so first detail we're going to talk about is how we represent it. So we mentioned we represent it with an array. But if you remember from a few lectures ago, when we were talking about, or maybe it was even the last one, or not lectures, but like discussions ago, we were talking about how to represent just a binary tree in general as an array. And that's just all we do with a heap. And a lot of times it's easier to do one indexing than zero indexing, but we can do zero indexing as well. That's completely fine. And these are just the general guidelines to follow. Is the left child for one indexing is 2i. Like if you're at index I, the left child of it is 2i, and the right child is 2i plus 1. And the parent, if you want to go back, is just I divided by 2. But with zero indexing, you have to adjust it slightly. So for the left child, it's 2i plus 1, and right child is 2i plus 2. And then you need to subtract 1 also if you find the parent. Okay, but now we can kind of see here the array representation of this heap. So 1 is our root, right? And let's just treat it as if it's one index, just because it's easier. But zero indexing is also okay. It's going to get the same result. So let's label the indices here: 3, 4, 5, and 6. So our first element is 1. So 1 is the root. So put 1. And so let's even make our own tree so we can kind of see how we get to this point. So 1 is the root, and then 3 is, we have 1's children are in index 2i and 2i plus 1. So that's going to be 2 and index 3. So its left child is index 2. Its right child is index 3. And then now we go ahead and keep going. So 3's left child is an index 2 times 2, which is 4. So that's going to be the 5. And its right child is 2 times 2 plus 1. That's this 9 here. And with 6, that's index 3. So 3 times 2 is 6. That gives us 8. So its left child is 8. And its right child, well, is past the end of the array. So its right child is going to just be null. That's pretty cool, right? Because if we just look at this, like visually, if we're building the tree this way, or if we represent it with an array, it's always going to be complete, right? Because the only things that aren't going to have children are ones, like the only things that won't have children are the second to last level, and it'll only be the ones as far right as possible, like only ones off to the right. Everything left will have as many children as it possibly can. So this representation of heaps will always give us a complete tree. So it'll always give us like a valid heap. And it's also really nice to work with. We're going to see why too. Hopefully that makes sense. And yeah, so now here's a question for you. What are the left and right children of 41? Here it's 0 indexed, so maybe it's a little bit hard to see, but yeah, what are the left and right children of 41?
The left child is 21 and the right child is 40?
Yes, that would be right. Yeah, sorry.
That would be if it was a 1 indexed.
Yeah.
So since it's 0 indexed, it would be 33 and 21. I mean,
oh yes.
I don't know.
That's okay. It's okay. We'll go through it. Don't worry about it. Yeah. So I think it's always easier if it's 1 indexed. We can also go back and look at the table for 0 indexing, but I think it might be easier to just 1 index it. But yeah, for left child and right child is 2i plus 1 and 2i plus 2 for 0 indexing. So let's just do it both ways, I guess. So first of all, I'm going to renumber them because I think that just makes my life easier. Okay, so if we renumber them, now we see 41 is now 3. So 3 times 2 will give us 40. As its left child, and its right child will be 35. But with the 1 indexing, that we can also do. Or sorry, with the 0 indexing. With 0 indexing, we see 41 here. So we have to find that the left child has 2i plus 1. So it's going to be at index 5. So its left child, we still get 40. And 2i plus 2 is the right child. So we still get 35 as the right child. So either way, you can get to the answer. I think generally one indexing makes life easier, but zero indexing, you just have to adjust the indices. With most representations of heaps, though, you will see one indexing just because it's easier to manage. But the answer should be 40 and 35. And notice that, like, unlike with a binary search tree, right, where like 40, like you have to have the left child to be like less than. Here it doesn't matter. Like all that matters is which level you're at and who your parent is. I guess this, yeah, this would be a heap because 41, its children are still smaller than it. It's valid maximum. Okay, so now the right and left child of 41 here. And notice that it's zero index.
The left child would be 72 and the right child would be null?
Yep, that's exactly right. And the way we get to that is, as Rachel mentioned, right, we have 41 here, and it's zero index, and that's important to notice. So 4 times 2 plus 1 gives us 9, that's 72. And 4 times 2 plus 2 gives us 10, and there is no 10, so it's null. So we have 72 and null. So, yep, exactly. Okay, and then question 3. What are the parents of 71 and 7?
So the parent of 7 would be 5, and the parent of 71 would be 30?
Mm-hmm. Yep, exactly right. So again, as Rachel mentioned, in order to get there, right, the parent of 7, well, when we want to find parents, we have to do, and it's zero indexed. For zero indexing, we have to do I minus 1 over 2. And here, for 7, it's going to be 1 minus 1 over 2. And we do integer division, so even if we're like 15, that'd be 2 minus 1 over 2, 1/2, we round down. But in the case of 7, that's just 0 over 2, which is just 0. So we look at index 0, that's 5. And then for 71, we do I minus 1. Well, I is 9, so 9 minus 1 is 8, over 4 is 2. And over 2 is 4. And so we should get 30 as the parent of 71. Okay, cool. So now we can move on to what kind of operations does a heap have? Well, there's heapify. And heapify, what does that mean? Well, heapify is an operation in which you rearrange the heap, and you maintain the heap property. So basically, heapify, if you call heapify, you're going to make it into a heap if it's not already. So there's heapify up, heapify down, and just heapify. So we call heapify at the beginning. Well, you can call heapify just like repeatedly to turn or to just make something into a heap. But then there's also heapify up, which is something you have to do after inserting in order to fix the heap. Because after you insert elements, you may not have a valid heap anymore. Because let's say you add something to the end of the heap, right? And the array representation, that means you add it to the end of the array. But if we think of it as a tree, because you have to think sometimes of a heap as like a tree and sometimes it's an array. It's really just both, they're the same. But I think sometimes it's easier to think of it one way or the other. But anyway, after inserting, you add it to the end of the array. You also add it as the last place in the tree. So let's say you have like a max heap, and the thing you add that's last is a really large element. Well, then it should be close to the top, right? Because in max heap, you have the largest elements at the top. But if you add it right to the end, well, you need to move it into the right position somehow. So you need to move it up the tree. So that's what we have to do. And that's what heapify up is all about. We'll see an example of that in a minute. Heapify down, after removing an element, you need to somehow fix it, like fix the tree. So the only element, if you remember, the only element you can actually remove from a heap is the root, right? So when you remove the root, now something else has to take its place. So when we do that is we take the last element in the heap, put it at the root, and then move that last element down until it gets to the right position. And then it's a valid heap again. We'll see an example of that too. So let's see examples. So first of all, insertion. So we're going to start just looking at a max heap. Again, anything we look at with a max heap, it's going to be the same with a min heap. It's just instead of the largest element being at the root, it's the smallest element. With a max heap, it's the largest, right? Okay. So here we have, this is our heap, and this is the array representation. So sometimes it helps to have both representations. So the first thing we're going to do is we're going to do an insertion. So let's say we insert 45. So we already saw what it's going to look like, but let's walk through what happens when you insert 45. Well, actually, we didn't really see. So yeah, the first thing you do is this. You insert 45. So 45 is going to go, for insertion, you just add it to the end of your array. And when you add it to the end of your array, in terms of the tree representation, that just looks like adding it to the last available, or the first available place. So if it's a complete tree, the next available place before was just the right child of 35. Because you have to add 45 as a leaf, but as far left as possible. And that's right here, to the right of 35. Okay, so this is the representation, this tree representation, insert 45, but it's not a valid heap. And it's not a valid heap because 35 here, in order to be a heap, every node has to be larger. In order to be a valid max, every node has to be larger than its children. 35 is less than 45. So it's not a valid heap. And so we need to fix that. So we do that is we do heapify up. So after insertion, we do heapify up. And what that means is we just keep moving the new element that we inserted, keep moving it up the tree until we reach a point at which it doesn't need to move anymore. So let's see what's going to happen. We insert 45. So we check 45 versus 35. And the way we do that in terms of code, like in terms of just the picture, we check, okay, the parent, it's very easy to see, right? But in terms of code, that's where the array representation is really nice. Because we know that the parent, if we're using zero indexing, we know the parent of 45. We know the new index, right, is like 0, 1, 2, 3, 4, 5, 6. We know the new index is 6. And we can figure out its parent by just doing 6 minus 1 over 2. And so in terms of code, we just check the array at index this versus array at index 6. So that's all we need to do. And that's really nice about having an array representation. But what we're doing now is we're checking 45 against its parent. And this is just how we find the parent. It's like this. But once we found the parent, we just check 45 against its parent. And if it's a max heap, then if it's larger than the parent, we need to swap the values. Because 45 is larger, if 45 is larger than 35, then 35 has to be a child of 45. And so that's exactly what we're going to do. We check them. If 45 is larger, we just swap. So we do a swap. And we swap in the array, which will just, in the tree representation, will just look like you swap them also. So now we can see that. All you do is swap. That's it. And now we get the new index for 45. And for 45, now we check it against its parent. Now its new parent is 50. So again, that's just the current position. If we're doing zero indexing, current position minus 1 over 2, we check if 45 is larger. If it is, you swap. And you keep swapping until you reach the root. Well, here there's no need for that because 50 is larger than 45. And so we don't swap and we're finished. And this is just the code for it. And maybe you can kind of realize that insertion is going to be log n, because if we look at just the tree representation, when you insert an element, you insert it at the end of the tree, like at the last place. And we know the height of the tree is log n. And in the worst case, all we do is we keep moving up the tree and move up and check it at every single level. At every single level, we make one check and maybe one swap. But a swap takes O1 time and a check makes O1 time. So we just have, and the height is log n. So we're only checking for log n elements up the tree. We're making an O1 time check. So it's 1 times log n. So the time complexity of insertion is just log n. And this would be the code for it. So to insert the new element at the end of the array and set the child to array size -1. So you just insert, okay, so you insert the new element at the end of the array and its current position is like the end of the array size, right? And then you set the parent of it to whatever index it's currently at, -1 over 2. So that's the same thing as we mentioned before, zero indexing, right? You find this parent index. And while the parent is greater than zero, and what this check does, it makes sure that like if you reach the root, you can't go any further. So once you reach the root, you can't swap with anything. So while your element is not the root yet, and you haven't reached a point at which the parent is larger than the child. Because if the parent is larger than the child, you also don't keep swapping. You're just done. But as long as one of those things is not true, then the child must be larger than the parent. And if it is, you swap them. And then the child index becomes the new place it's at, and the parent index becomes the previous one's parent. So in terms of this, right, after swapping 45 and 35, the child index is now where the 35 was, and the parent index is now where the 50 is. So that just allows us to check 45, like after 45 moves off, it allows us to check 45 against 50. And that's what's going on inside this while loop. And that's it. And I realize that might sound like a lot of words, but if you just, maybe if that was confusing, if you just look at this, maybe it'll make a little more sense. And look at the example as well. Okay, but a question. Assuming 21 was just inserted into this heap, after adjusting nodes, what location would 21 be in?
It would be in position B.
Yep, that's exactly right. It would absolutely go into position B. Because if we notice, this looks like it's a max heap, right? And it's max heap because every node is larger than its children. So you just inserted 21. Well, it's not quite a valid max heap because 21 is smaller than 19. So we move 21 up and swap it with 19. So it becomes 21. This becomes 19. And now we try and swap 21 with 32. We can't, right? 32 is larger, and we're done. So 21 finishes in position B. No, position B. Okay, so now we're talking about deletion. And deletion is kind of similar in the sense that some of the things you have to do for deletion, right? You still have to, like, some of the things we talk about with insertion are still true of deletion, in that you still have to like kind of go through the tree and fix the heap. Except instead of heapifying up, like we do with insertion, you have to heapify down. So, okay, first things first. When we delete something from a heap, the only thing we can delete is the root, because the only thing we have access to is the root. And I know we've gone really far from priority queues, but I just want to bring it back to priority queues for a second. So heaps, really, we haven't gone so far from priority queues in the sense that heaps just are, our priority queues just are heaps in general. Like the way we write a priority queue is just using a heap. That's generally it. So we're not really too far from there. I just wanted to bring that point back in case anyone was confused about what happened to priority queues. Okay, but for deletion, so the priority queues with heaps, you only have access to the one element, the root, right? They're the smallest element with, like, or the element in this case, the min heap, right? The element with the highest priority. It's the smallest element here. So that's a 3. And so we're going to remove a 3. That's the first thing we do, is we just remove the 3, it gets out of the tree, and then we're left with like 2 subtrees, the right side and the left side. And what we do next is we move the 43, we move the last element in the whole tree from before and make it the new root. So that's what this is going to look like. We delete the 3 from the tree, and notice there's nothing here. So then we're going to take the last element and put it into the beginning. And that's it. So we move 43 up. We don't move it up step by step. We just take it wherever, we take the last one, wherever it was, and put it at the root. So far, our operations have just been taken one time. Also, that's something we can keep in mind, right? So far, only taken one time. Because we're moving an element, well, we just didn't do anything with it. And 43, it takes one time to take the last element from the array and put it in the first position. So basically just take the last element in the array, put it in the first position, right? So like take the 43, move it to position 0. No, that doesn't take much time at all. Okay. But now we don't have a valid min heap anymore. That's not valid because 43 is larger than 7, larger than 12. So we need to move 43 down the tree in order to get back to a valid min heap. But which way do we move it to? Are we going to move it to the 7 or 12? Well, the way we choose is we have to remember that once we move something up to here, right, whichever one it is, that thing has to be smaller than both of its children. So if we chose 7, or if we chose 7, 7 has to be smaller than 43 and 12. If we chose 12, 12 has to be less than 43 and 7. So 12 isn't any good. So what we choose is we take the minimum of this one, and this one. Whichever one's smallest becomes the new group. And we can just do this recursively through the tree until 43 reaches the right position. So we're going to see that happen. We're going to see it play out right here. So we take the minimum. 7 is smallest between 12, 43, and 7. 12, 43, and 7. 7 is smallest, so it becomes the root. Check 43, 7, and 12. 7 is smallest, so it becomes the root. And then we swap 7 with 43. Okay, perfect. Now we just keep going. We go recursively. We check 43 against 11 and 15. Whichever one's smallest becomes the root of the subtree, and 43 moves down. Unless 43 is smallest, then it doesn't have to move. Well, we check. Oh, 11 is smaller. Okay, so it becomes the root of the subtree. And now 43 has reached a leaf, so we can't go any further. And notice that what was playing out in the array here was just we were checking the child indices, because in insertion we had to check the parent indices. Here we're checking the child indices. And now we're done, because the children of 43 are null, so we can't get to them right in the array. And then, yeah, that's it for deletion. And notice that it also took log n time, because again, the original check we had to make was moving 43 to the root and removing 3. And that took O1 time. Then we had to move 43. We had to find the minimum of 3 values at each level. And that takes O1 time each time. And they're log n levels. So O1 times log n is just a log n operation. It's log n O1 operation, which takes log n time. So for deletion, we mentioned that there's a recursive structure to it, right? And that's exactly what we see. Is to delete the minimum, first you put the thing in the first position, you take from the last position, and you call heapify down from position 0. So that means at the root, you're going to heapify down. And basically, just if the index is a leaf, you stop, right? So if its children don't exist in the tree, and then you find the smallest child of the index. And if the smallest child is less than it, then you swap them. If the smallest child is greater than it, then you don't make a swap, right? Because you're already done, like it's already a valid min heap. But if the smallest child is less than it, you swap them, and then you keep going, you heapify down from the next position, and that's it. So it's just recursively going through and deletion. So for question 5, assuming this heap just removed its root, what node is going to take its place before you call heapify?
D37.
Exactly. Yes, that's exactly right. Let's take the last one and move to it. So the right one. Yep. Cool. Then you're in heapify. And so heapify turns a binary search into a heap. You can also, this is another application of heapify. Turning a binary search tree into a heap. And this is going to look kind of confusing until we actually see what it all means with an example. But let's say that we're given a min heap, or we want to make a min heap. So we're given a binary search tree. So the first thing to do is iterate through the tree with an in-order traversal. Now, the thing about an in-order traversal in a binary search tree is it's always going to give you an ordered list, like a list of elements in like numeric order. So all this is saying is like, okay, give us a list of elements in just number order. So it looks more confusing than it is, but that's all it's saying. And then pass through the tree with the pre-order traversal. And now that might seem kind of weird, but we'll go through an example and we'll see why that works. And then for each node you pass, replace it with the node of the inner traversal with the same index. And that probably also sounds confusing, but don't worry, 2 and 3 will make a lot more sense when we go through an example. So I think an example next, rather than trying to explain it here, will be better. And the takeaway is that for a max heap also, it's the same thing. You do an inner traversal followed by a post order. So you replace the elements with post order rather than a pre-order. But that's the difference. Like there's not, it's pretty cool, right? Using in order and pre-order. So let's see. How do we turn this tree into a heap? Well, notice it's a valid binary search tree. So first things first, let's do our inner traversal. And like I mentioned, it's just going to give us the elements in sorted order. So 3, 8, 9, 10, 13, 15, 18. So ascending order, right? But remember that for a pre-order, now we're going to do a pre-order traversal because this was we wanted to do a min heap, right? Or I think we want to do a min heap. Let me see. Yeah, we want to do a min heap. So what's that going to do? Well, remember that for a pre-order traversal, that's node left, right? For pre-order. So we're going to insert a node, right? And then we're going to go left, and then we're going to go right. So since this is sorted, the node that we insert for each subtree, the node we put there is going to be smaller, like because we're going to put the element, right? Before we get to anything else, the node we put there is going to be smaller than anything comes after it. So at each subtree, this node is going to be smaller than all of its children. And that's true for every subtree in the tree. And as a result, it's going to be a valid heap. It's going to be a valid heap because with a heap, for a min heap, the only requirement is that every node is smaller than its children. And that's exactly what this defines. Whereas if we wanted to make a max heap, that's left-right node for post order. And what this is going to do is going to visit the leaves and going to put the elements from here into leaves before it puts them in the parent. And what that means for us here is that because it's going to put the leaves first and then go up the tree, it's going to put the smaller elements below the larger elements. And that's going to be a valid max. So that's why this works. But looking at the example, I think also is good. So doing a pre-order traversal to replace the nodes. So, okay. So our pre-order traversal is going to do this. So the first thing we do is we're going to go on the root and say, okay, node left, right. Well, when we see node, rather than printing out the value 10, like we would with a regular in-order traversal or regular pre-order traversal, when we see node, we're just going to put whatever element is next from this array. So in this case, we're going to put a 3. And now we have left and right. So let's go to the next slide. So we can so yeah. So now we have node crossed out with a left, right. We have left crossed out. And on this one, we're going to do node left, right. Well, the next thing we have to put in is 8. So when we see node here, we put 8. Let's put the 8 in the tree. And that's really nice and helpful because notice that because 8 came after 3 in the in-order traversal, it's going to be larger than 3. It has to be. And we're putting it under 3. So it's going to be larger. That's good. So let's kind of just see the in-order traversal play out. Or pre-order traversal. So 3 and then 8. And the next thing is going to be 9. So 9 is going to go on the left of 8. And that's also good. It's going to be a child of 8. It's larger. Cool. Now 10 is going to be the right child of 8. And it's larger than 8. Perfect. So notice the whole left subtree is done. But the same thing is going to be true of the right subtree, where 15 is the root, but it's going to get the first of these values. And then its children are going to get values that come after it in the in-order traversal. We're going to put these values afterwards. And these values are larger than this 13. So it's going to be valid min heap. And that's exactly it. And yeah, so I know all that seems kind of strange why we do that, but it's just an interesting result, and an interesting way to build a min heap from a binary search tree. But okay, creating an array in place. So the interesting thing about heaps though is if you're given just a random array, right? In order to build a heap, it might seem kind of okay, we know that we already discussed the insert into a min heap or max heap or just insertion into a heap in general takes log n time, right? Log n time. And inserting, and we want to insert n elements, right? Let's say we want to make a heap. Well, the way we would do that is we just insert all n elements into the heap, right? So insert n elements. Each one takes log n time. So building a heap should be n log n time, right? But that's not quite the case. You can actually do it a little bit faster. You can do it in no n time. And the reason for that, I won't get too much into the details, but I'll just give a brief overview of why. If you want to see more math, you can do it here. You can look here. But you can actually do ON, and the reason for that is you can insert basically from the bottom up. And remember, it's a complete binary tree. So what that's going to mean is that we have something like this. Let's just, for sake of argument, assume that it's a perfect binary tree. So one structure of binary trees that we notice is that the last level, they're n/2 nodes. And at the second to last level, they're n/4 nodes. And the level before that, they're n/8 nodes. And if we insert from the bottom and go up the tree, then at the last level, we only have to move, like if we're putting elements into the heap, we only have to move up 1. Like we don't have, or 0, I guess. We don't have to move up at all. Because wherever we put the element is where it goes. We don't have to move, we don't have to like worry about going up the tree. So it's like 0 to the total number of operations. You don't have to know the math. I'm just going to go over it anyway. I want you to at least get like a general understanding of what's going on here. So you have to move 0 times up the tree, plus 1 time up the tree for each of the n/4 nodes, plus 2 times up the tree for each of the n/8 nodes, plus 3 times up the tree for n/16 nodes. And it's not so easy to maybe show it, but the important result here is like this sum, right, is just like, yeah, it's gonna be like k times n/2 to the power of k plus 1. That's what the sum is. And it's summing over how many levels there are, which is just log n levels. And okay, and this sum converges to a multiple of n. That's the thing. And again, this isn't so important. I just thought it would be nice to kind of show you that it really is O(n) time and not O(n) log n. But okay, that's not so important that you know that. Okay, in terms of building a heap though, if you want to build a heap, you can just, it's nice, even if it's an empty array to begin with, in order to create a heap in place, all you have to do is just insert the elements and call heapify down. Or just insert the elements via heapify. So you insert an element, call heapify, and that's it. And if you do that recursively, or just not recursively, if you do that for every element, you'll have a heap with all your elements. And that's how you can build a heap. Okay. So that's everything. I know that was a lot of like random stuff, but hopefully that made sense. And hopefully that kind of covers heaps and predicate. And here's some resources. And yeah. So, do you guys have any questions?
No, thank you.